Hi students, welcome. In this video we will study about constant volume process. Okay, so here first we will see about definition of constant volume process. So here, if any system of gas undergoes a process in such a way that during the process the volume of the system remains constant, the process is called constant volume process, or it is also called as isochoric process. Okay, so see here in the PV and TS diagram, here this is a PV diagram and this one is the TS diagram. On PV diagram, as this is a constant volume process, so here it is a straight line and it is a cooling process. As you can see here, this is the pressure P1 at this state 1, okay, and here this is pressure P2 at this state 2, and here this straight line indicates that it is a constant volume process. Okay, and on TS diagram, as you can see here, this is the state 1 and here this is the state 2. Temperature is decreasing, that is, this is here the here cooling process. Okay, as you can see, state 1 to state 2, temperature T1 to temperature T2, temperature is decreasing, so here this is a cooling process. And now see here the example of this constant volume process is here. It is this process is taking place in a pressure cooker, gas cylinders, etc. Okay, and now see here, we will see here property relationship of for constant volume process, and here this is our general equation of property relationship, which is P1 V1 upon T1 equal to P2 V2 upon T2. Here this term, and here as we know volume is constant, so here V1 is equal to V2. Okay, now as V1 is equal to V2, this our general equation simplified as now here as this one, like P1 upon T1 is equal to P2 upon T2. This is a property relationship for constant volume process. Okay, and now further here we will see now work done during process. So as we know here, this constant volume process is for non-flow process, or you can call it as non-flow system. Okay, and here work done can be calculated from the PV diagram also, when the area by the area under the curve. Okay, that is, as here you can see, this is a straight line, so here there is no area under this curve. Suppose here this is a PV diagram, okay, and here the process is like this. Then here you can see there is a volume V1 and volume V2, so here there is a area under the curve and this area is called here work done. So here in this case, that is constant volume process, as you can see here there is no area under the curve, so here work done for constant volume process will be 0. So here see, this work done, that is for state 1 to state 2, is equal to 0, and we can calculate it mathematically also. So for this W1 to 2, W is denoted is now a symbol for work done. Okay, so W1 to 2, that is process 1 to 2, is equal to integration of 1 to 2 P dV. Okay, as here this is constant volume process, dV is equal to 0, so from that we will get here this work done is equal to 0. Okay, now here we will see now change of internal energy. So change of internal energy, so here this is delta small u signifies us that, tells us that this is a change in specific internal energy. Okay, change in specific internal energy is equal to CV into bracket T2 minus T1. Here this CV is our specific heat at constant volume, and T2 minus T1 is the change in temperature, and this change of specific internal energy is given, is its unit is kilojoule per kg. Okay, this is our specific internal energy, that is delta small u is equal to Cv into bracket T2 minus T1. And now here change in internal energy, this one is small u is specific internal energy, and this capital U is our change in internal energy. Okay, now see here delta capital U, that is change in internal energy, is equal to m, as you can see here delta capital U is equal to mCv into bracket T2 minus T1, and its unit is kilojoule. Okay, and here this small u, delta small u, that is specific internal energy, is based on unit mass. Okay, unit mass, as that means here when we put here mass is equal to 1, we will get here specific, when we put mass is equal to 1 in internal energy, change in internal energy, then we will get here specific internal energy, as you can see here, and because of this kilojoule unit becomes here kilojoule per kg. Okay, now see here we will see calculate here heat transferred. So for this heat transferred is given by capital Q, which is equal to m Cv T2 minus T1, and this is equal to change in internal energy. As we have seen here, this also the same term and this also is the same term. So as we can see, we can call it like Q, that is heat transfer, is equal to change in internal energy, we can call it. Okay, heat transfer is equal to change in internal energy. So here now again for in unit mass basis, this heat transfer will become small q is equal to Cv T2 minus T1, which is equal to delta small u, and its unit is kilojoule per kg. Okay, now further here change of enthalpy. Okay, change of enthalpy is given by delta small h is equal to Cp T2 minus T1, and its unit is kilojoule per kg. It is in unit mass basis, that is specific change of specific enthalpy, that is delta small h is equal to Cp T2 minus T1. And now change of enthalpy, that is delta capital H is equal to m Cp T2 minus T1, and its unit is kilojoule, and here this Cp is specific heat at constant pressure. Okay, now further here change in entropy. Change in entropy is given by this delta capital S, which is equal to mCv ln, this is the symbol for ln T2 upon T1, and its unit is kilojoule per Kelvin. Okay, now for unit mass basis, this change in entropy will be change, and we call it as a change in specific entropy, that is delta small s is equal to Cv ln T2 upon T1, and its unit is kilojoule per kg Kelvin. Okay, so students, in this video we have understood about constant volume process. Thank you students for watching this video. Like, share and comment for this video, and subscribe my channel. Thank you.